Section: Introduction. In this section, we outline the key elements of the standard reinforcement learning from human feedback (RLHF) post-training process, summarize the self-taught reasoner (STAR) method, and review the concept of using large language models (LLMs) as judges. First, we discuss supervised fine-tuning (SFT). In this initial stage, we train an LLM to follow instructions using a dataset of prompts and responses, applying maximum likelihood estimation to predict the next token. The resulting model is denoted as pi_SFT, treating both prompts and responses as single variables. This model serves as the foundation for subsequent stages. Next, we move to reinforcement learning (RL). In the final stage, we utilize a learned reward model to optimize the LLM through an on-policy RL algorithm, like proximal policy optimization (PPO). Our aim is to enhance the LLM's responses to align with human preferences. The optimization focuses on minimizing the Kullback-Leibler divergence, which helps maintain the LLM's original behavior while balancing the exploitation of the reward model. We then introduce the self-taught reasoner (STAR) method, which employs an iterative bootstrapping strategy to enhance the reasoning abilities of LLMs. STAR emphasizes training models to create and refine rationales, especially for complex reasoning tasks. For rationale generation bootstrapping, we assume access to a dataset of questions requiring strong reasoning and their corresponding answers. We prompt the model to generate both a rationale and an answer, filtering the results to keep only those rationales that lead to correct answers. This filtered dataset is then used for further training with the standard SFT objective, and we repeat this process over multiple iterations. To address the limitation of not improving on initially incorrect examples, STAR incorporates a rationalization process. When the model produces an incorrect rationale and answer, we provide the correct answer as a hint, allowing the model to generate a new rationale based on this information. This synthetic data is then integrated into the STAR training objective. Finally, we propose a unified RLHF/RLAIF framework using generative reward models. Here, we start with an LLM acting as a zero-shot judge, prompting it to indicate preferences between two responses. We explore two variations: the generative reward model, GenRM, which directly provides answer probabilities, and the GenRM, which includes intermediate reasoning before the final answer. We design various training techniques for the generative reward model. For GenRM, we apply standard supervised fine-tuning. For GenRM, we consider bootstrapping reasoning from ground truth or a stronger rationalization model. We also explore a self-bootstrapping approach using STAR, employing different loss objectives based on the quality of reasoning chains. This leads us to create a dataset of preference pairs, allowing us to optimize the model using a DPO objective. Section Summary. In this section, we outline the standard reinforcement learning from human feedback (RLHF) post-training pipeline, introduce the self-taught reasoner (STAR) approach for enhancing reasoning capabilities in language models, and review the LLM as a judge framework for preference evaluation. We detail the stages of supervised fine-tuning (SFT) and reinforcement learning (RL), emphasizing the iterative bootstrapping and rationalization processes used in STAR to improve model performance on complex reasoning tasks. Section: Experiments. In this section, we evaluate how well our generative reward modeling approaches perform compared to traditional Bradley-Terry reward models, a newer variant called pair-RM, and zero-shot RLAIF evaluation. All models utilize the LLAMA 3.1-8b instruct model. We use two training datasets: Ultra Feedback, which contains 61,000 pairs focused on general instruction following, and Ultra Interact, which includes multi-turn reasoning tasks in math, code, and logic, featuring advanced skills like tool use and environment interaction. We assess the models on both training datasets and on Reward Bench, a benchmark with 4 subsets: chat, hard, reasoning, and safety. Detailed training information is available in the appendix. Our experiments aim to answer several questions. Do generative reward models perform as well as classical models? How robust are these models, and how well do they generalize to out-of-distribution data? Does reasoning enhance reward modeling, and can we leverage inference time computation for better results? Do we need strong reasoning data to train generative reward models, or can we derive reasoning from the model itself? For our first set of results, we show that all models trained on the ultra-feedback dataset were evaluated on a held-out in-domain split and reward bench. We first looked at the zero-shot performance of the Llama 3.18b instruct model as an evaluator, using chain-of-thought prompting with self-consistency and acting as a classifier that directly ranks responses. We found that prompting the model to reason over answers significantly improved its performance, raising accuracy from 52.25% to 67.75% on ultra-feedback and from 60.60% to 75.18% on reward bench. However, when we compared these zero-shot methods to trained models, we discovered that both approaches performed worse than the Bradley-Terry-Erm, pair-RM, and trained GenRM models, which all had similar accuracies around 73 to 74%. The STAR DPO model matched these accuracies at 73.9%, while the STAR SFT model only achieved 67.4%, showing no improvement over the base model. When we evaluated these models on out-of-distribution tasks, the STAR DPO model performed best, scoring 81.9% compared to the base model's 77.8% and the trained RM's 78.9%. The STAR DPO model consistently outperformed or matched the baselines across all reward bench categories, while the STAR SFT model did not show significant differences from the base model. The GenRM model outperformed both the Bradley-Terry-Erm and pair-RM, achieving performance similar to STAR DPO across chat, hard, and reasoning. Notably, reasoning-based approaches excelled in the safety category, with STAR DPO achieving 91.0% accuracy compared to pair-RM's 81.8%. We also evaluated performance on reasoning tasks by training models on the UltraInteract dataset, which focuses on complex reasoning evaluations. Our findings showed that the STAR DPO model outperformed STAR SFT on the UltraInteract evaluation dataset, achieving 90.2% compared to 68.8% for the base model. While this was slightly lower than the explicit ERM models, which scored around 94%, we observed a divergence on the reward bench evaluation. The Bradley-Terry-Erm, pair-RM, and GenRM struggled to generalize, with the best GenRM model only achieving 70.8% accuracy, worse than the Llama as a judge's 76.6%. In contrast, the STAR DPO model significantly outperformed both baselines with 87.2%, demonstrating its ability to generalize meta-reasoning skills to different reasoning prompts and answers. On non-reasoning evaluations in reward bench, the Llama as a judge achieved the highest accuracy at 78.0%, while explicit reward models struggled. The STAR DPO model only experienced a slight drop in accuracy to 75.0%. Overall, we found that the STAR DPO model outperformed the base Llama as a judge and the GenRM model on held-out tasks in reward bench. We also explored how to generate the reasoning chains used for training. We sampled rationales using a star-based approach with the same base model. We then evaluated a method that samples rationales from a post-rationalization model, which we call Star Rationalizer. Results showed that the Star Rationalizer matched the performance of the Star DPO model on both datasets, significantly outperforming the Star SFT approach. However, it struggled to generalize to reward bench tasks, performing worse than both the STAR DPO model and the base Llama model. This suggests a potential issue with distribution mismatch during training, as the rationales from the post-rationalization model may not align with the base model's training distribution, leading to challenges on novel tasks. Section Summary. In this section, we evaluate our generative reward modeling approaches against classical models and zero-shot evaluations using two datasets, UltraFeedback and UltraInteract, as well as the reward bench benchmark. Our results show that the STAR DPO model excels in both in-distribution and out-of-distribution tasks, particularly in reasoning capabilities, outperforming other models, while the STAR SFT model shows limited improvement over the base model. Section: Related work. In this section, we discuss the growing interest in using language models for feedback, often referred to as constitutional AI or RLAIF. The concept of LLM as a judge has gained popularity, showing that strong language models can make judgments using chain-of-thought reasoning that resembles human evaluation. We build on this by introducing Prometheus, which uses supervised fine-tuning from a powerful model to enhance reasoning and scoring, achieving impressive evaluation results even with a smaller open model. Our findings indicate that zero-shot evaluations from language models may not completely match human feedback, and we can significantly improve accuracy through additional fine-tuning. Our approach combines RLAIF with STAR-based tuning without needing ground truth reasoning or supervision from a stronger model. At the same time, another study introduced generative verifiers, which train a model to verify mathematical reasoning using a specific objective. They observed similar results to ours but depend on having complete reference solutions during training, which sets them apart from our method. Additionally, another concurrent work merges chain-of-thought reasoning with a specific reward modeling approach. They present findings that align with ours but rely on a separate strong model for rationales and a hybrid architecture, while we utilize self-bootstrapped rationales in a comprehensive language modeling setup without needing extra architecture. Several other studies have also explored self-bootstrapping generative critics. One approach is akin to our STAR SFT method, using data augmentation to create synthetic preference pairs. Another employs a different optimization method for the evaluator, relying on an additional meta-judge. Similarly, some generate data through various augmentation techniques and use a specific training method. We believe these data generation techniques complement our focus on STAR-based methods to align generative reward models without explicit reward models.